Hi there, welcome to lecture 17 of FOCS. We're going to be talking about independence, which is an assumption that sometimes we can make that simplifies the computation of probabilities. But as usual, before we get going, let's quickly recap what we did last time. Okay, last time we were talking about conditional probability. So this is a very important topic. It's how do you update your probability when new information arrives? And it's very important to always be, taking into account all the information that's available about the experiment so that you can compute the correct probability, the correct chances of whatever you're interested in happening. Okay, so we developed, just like computing probabilities, computing conditional probabilities reduces to computing probabilities, and so you can, mechanically compute the probabilities based on the sort of definition, and then the interpretation is that it's the updated probability to take into account the new information. Now, conditional probability is subtle, and it's possible to fall into several, different types of, traps, conditional probability traps. We talked about sampling bias, we talked about the transposed conditional using probability of B given A instead of the probability of A given B, and its application to medical testing. Okay, and then we ended last lecture with a very simple principle, the law of total probability. It's a simple principle. It says, it gives a formula for how you can break down an event A into two events and then sort of add up weighted, probabilities to get the probability of A. This law of total probability is simple, but it is very important. Okay? It's sort of a case-by-case analysis, technique for probability. And, we can use it for build-up probability, just like build-up counting. We can use it to simplify the analysis of, computing probabilities when things can go on forever, if they repeat. And we can also use it to just compute the probability of more complex events. Okay? So that's conditional probability. Make sure you read the chapter carefully. I mean, it's a very important chapter. Lots of problems, lots of exercises, lots of pop quizzes. Do them. Okay? And today we're going to be talking about independence. Okay? And I want to emphasize that, independence is not a theorem or an axiom, it's an assumption. Some experiments you can assume independence, in some experiments you cannot. Okay? And now we'll talk about various applications of independence. Starting with the Fermi-method, which is a very good technique for approximating things. Okay, and then we'll talk about the birthday paradox, which has an application to one of the most famous algorithms in computer science, hashing. Without hashing, lots of practical applications just would take too long. Okay, and then we're going to talk about the random walk, okay, and the gambler's ruin problem. And you definitely want to avoid the gambler's ruin. Okay, so let's move to the board and get going. Okay, independence. And I want to emphasize that independence is an assumption. So you cannot assume it in general for whatever problem you're working on. Okay, so independence. Okay, it's an assumption. And sometimes it holds and sometimes it doesn't. But when it does hold, computing probabilities can be much easier. So let's talk about what independence is. You're interested in two things, and these two things have nothing to do with each other. So what does that mean? Let's pin it down. Okay. So you have consider two kids, okay, from the same two parents. Okay, and the first is a girl. First is a girl. Okay, what's the second? A boy or a girl? So you should be looking at me and saying, "How would I know?" Okay, and that's key to independence. So telling you that the first is a girl tells you nothing about whether or not the second is a girl. And that's the prevailing medical opinion, that the sexes of, children, even within the same family, they're independent. Okay, so sexes of kids are independent. Okay, that's what we mean by have nothing to do with each other. If I tell you something about the first thing you're interested in, it doesn't tell you anything about the second. Let's take another example. Eye color. Okay, so the girl has blue eyes. What about the second kid? Does the second kid have blue eyes or not? And now you might think, I'm going to guess that the second kid has blue eyes. Why? Because if the girl has blue eyes, probably the parents have blue eyes and eye color is inherited. And so that suggests that the second kid also might have blue eyes. So key difference from the sex of the kids, boy or girl. Key difference. Okay. Eye color of the first child tells you something about the eye color of the second child. So eye color is not independent, even for kids in the same family. But the eye color of one kid in one family might be independent of the eye color of some other kid in some other family. So if I told you that, this girl has blue eyes, what are the colors of the children in my family? You'd look at me and say, oh, that doesn't give me any information. Okay? But in this case, eye color for kids in the same family, not independent. So now you see that independence is sort of a phenomenon that may or may not hold. That's why we say it's an assumption. Let's take another example. Flip 2 coins. So you flip the 2 coins. The first flips heads. Okay, so what's the second flip? Look at me and say, how would I know? That's the key to independence. So telling you something about the first coin flip tells you nothing about what the second coin flipped. Okay, and so the 2 coin flips are independent. Okay, so the 2 coin flips are independent. Okay, and usually, and we'll do lots of experiments with coins, and so we will typically say something like, you have 10 coins, assume that they're all independent. Okay, so you flip 10 independent coins. That means that whenever you flip one of them, it tells you nothing about the others. Okay, one more, last example. Okay, it's raining today, so we're interested in days where it rains and days where it's cloudy. So today's a rainy day. Today, okay, it's rainy. Okay, so I'm now interested in whether or not there are clouds. Question mark. Are there clouds? Look at me and say, yes, of course. Okay, because that's the way the world works. It can only rain if there are clouds. And so that what that tells you is that whether or not a day is rainy and whether or not a day is cloudy are not independent, because telling you something about one gives you an idea what's going on with the other. Not independent. Okay, so now let's mathematically pin this down. Okay, so let's take the case of 2 coin flips, which are independent. So independent coin flips. Okay, now we argued that they're independent intuitively on the basis that one flip doesn't tell you about another, but let's see what happens when you do the 2 coin flips. And let's say you do it 100 times. Okay, so you flip 100 times. The first coin will be heads roughly 50 times. Okay, that's what it means for the probability of, well, let's assume the coins are fair. That's what it means for the probability of heads to be 1/2. Okay, and now what's going on with the second flip? Okay, and the second coin, so 50 of them are heads, 50 of them are tails. Okay, and the second coin, says, I don't care what happened to the first coin. I'm going to behave independently. So no matter what whether the first coin was heads or tails, in either case, for these 50, roughly 25 will be heads, tails, and roughly 25 will be heads, tails. And we could ask, how many of these experiments came up heads? So coin 1 heads for coin 1. Let's write that as coin 1 heads and coin 2 heads. Okay. How many times does that happen? Is 25 times, and if we take the frequency interpretation of probability, 25 over 100 is, the probability that you get coin 1 heads and coin 2 heads, which is, 1/4. Okay. And then when we did the mechanical approach to probability, we said we're going to take, we put edge probabilities 1/4, 1/2, 1/2, and 1/2, and so on all the edges, and then we multiply the edge probabilities to get the outcome probability. So 1/2 times 1/2 is 1/4. So this is 1/2 times 1/2. So we get the probability of coin 1 heads and coin 2 heads is 1/2 times 1/2. But we observe that this is the probability of coin 1 head, and this is the probability of coin 2 head. Okay, and you're multiplying these two probabilities and you get the probability of coin 1 head and coin 2 head. And it turns out that, this notion of the and of the two outcomes is key to the definition of, the mathematical definition of independence. Okay, so now let's look at a situation where we didn't have independence. Let's say we look at, rainy and cloudy days. So not independent. Okay, so let's look at the chances of a rainy and a cloudy day. Probability of rainy and clouds. Okay, well, we did this last time. That's the intersection of the rainy days and the cloudy days. But every rainy day is cloudy. So this is, rain, intersection clouds. And this is equal to rain. Because every rainy day is cloudy. So this is just the probability of a rainy day. Okay, which is, where when we talked last time, we said that it's cloudy 1 in 7 days and it's raining it's cloudy 1 in 5 days and it's raining 1 in 7 days. Okay, so the probability of rain is just 1 in 7, which is also the probability of rain and clouds, but this is not equal to the probability of clouds times the probability of rain. It's not equal to 1/5 times 1/7, which is the probability of clouds times the probability of rain. Okay. And so we see in this situation where you do not have independence, the probability of the and is not the product. When you do have independence, the probability of the and is the product. And that ultimately is the fundamental definition of independence. But let's now pin it down in a more general setting. Okay. So, in a more general setting, you have your sample space, you have your experiment, for which you have a sample space and probabilities for each outcome. And so you can define two events, A and B. So you have events A and B, arbitrary events. Okay, and now let's see. A and B are independent. We say A and B are independent. Okay, now let's try to pin this down mathematically. If, knowing that B occurs tells you nothing about whether or not A occurs. Okay, so knowing that B occurs tells you nothing about whether A occurs. Okay, so if I tell you that B occurred, okay, thank you very much. If I tell you that the first child is a girl, well, thank you very much. It tells me nothing about the second child. Okay, what are the chances the second child is a boy? Still a half. If you think of getting children as flipping coins, and each child is equally likely to be either boy or a girl, heads or tails. Okay, so knowing that B occurs tells you nothing about whether or not A occurs. And now in the world of probability, that means that, initially there's some probability that A occurs. Okay, now I tell you that B occurs. That means I give you new information. And did that change the probability that A occurs? No. Okay, so that's the idea behind independence. And now we have a language for that, in the language of conditional probability. So we're saying that probability that A occurs, given some information about B, given that B occurs, does not change the probability that A occurs. So this is the probability that A occurs. It's not changed. Okay, and then we say that A and B are independent. That's the definition of independence. Now you might say, well, we talked about, the AND event multiplying probabilities. I claim that is equivalent to the statement that the probability of A and B occurring is the product of the probability. So let's prove that. Okay. Remember, the probability of A given B is equal to the probability of A and B divided by the probability of B. Well, that's what we said. Okay, we said that the probability, that's the definition of the conditional probability, the probability of A given new information. But now we're saying that when we have independence, so it's an assumption, it doesn't always hold. When we have independence, this guy is equal to the probability of A. So this guy is equal to the probability of A. Now let's just rearrange terms, and you see that we get that the probability of A and B is equal to the probability of A times the probability of B. Okay, so I'm going to box this. And I'm going to box this. Okay, so there you go. When you have independent events, knowing that one occurs doesn't change the probability of the other. That's what this says. Okay, and it is equivalent to saying that the probability that the two events occur, the probability that A and B occurs, is the product of the individual probabilities. Okay, so when you have independence, probabilities multiply when you're computing an AND. And that makes it sometimes very convenient to compute the probabilities of very complicated events. For example, probability that this happens, and that happens, and that happens, and that happens. Well, if they're independent, it's just the product of the individual probabilities. Okay, so let's erase and do lots of examples. Oh no, we dropped it. Okay, let's do an example and then I'll show you an interesting application of independence. Okay, so flip 3 coins. So the outcomes are H, 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 HHT, HT, HTT, THH, THT, TTH, TTT. Okay, so we're constructing the outcome space, and you can do the outcome tree and figure out that it's a uniform probability space, and the probabilities are all 1/8. Okay, so this is flip 3 coins. Okay, now I'm going to define 3 events: A1, A2, and A3. Okay, this is the event coin 1 and 2 match, coin 2 and 3 match, and this is A3 is the event coin 1 and 3 match. Okay, now formally as subsets of the sample space, so coin 1 and 2 match means that they either are both H, okay, so HHH, HHT, or they're both T, TTH, TTT. So there are 4 outcomes, okay, and the similar thing for event A2, coins 2 and 3 match, so you have HHH, THH, HTT, TTT, and coins 1 and 3 match. So HHH, HTH, THT, TTT. And we can ask what's the probability of A1, and that's the same as the probability of A2, and that's the same as the probability of A3. Okay, and because we're in a uniform sample space, we just take the size of the event and divide by the size of the sample space. So this is 4/8, which is 1/2. Okay, and now let's ask for some AND events. So the probability of A1 and A2 is equal to, well, we need to take the intersection. The intersection is the probability of the intersection is just HHH and TTT, the outcomes that are common, HHH and TTT. Okay, and so that's equal to 2/8 equals 1/4. And look, that's equal to the probability of A1 times the probability of A2. Because each of those have probability 1/2. So this is 1/2 times 1/2, which is the product of the probabilities. So A1 and A2 are independent. A1, A2 are independent. Okay, good. Now, you can do the same thing for A1 and A1 and A3, A2 and A3. So probability of A1 and A3 also equals 1/4. And probability of A1, A2, and A3 also equals 1/4. Okay, but now let's consider the intersection, the AND of all 3 events. Probability of A1 and A2 and A3 is equal to, okay, so we need the intersection of all 3 events. And you'll see that it's HHH and TTT is common to all 3 events. So it's the probability of the event HHH and TTT, which is the same as, what we just computed, 2/8. So this is 2/8, which is 1/4. Okay, but the probability of each individual event is 1/2, 1/2, 1/2. If you take the product of these 3, you get 1/8, not 1/4. So this is not equal to the probability of A1 times the probability of A2 times the probability of A3. Okay, and so that's interesting. So here's a situation of 3 events where any pair of them are independent, but the 3 of them taken together are not independent. Okay, and that's possible. It's even possible to find a situation where the 3 of them taken together are independent. So the probability of the AND of 3 events is the product, but then pairwise they are not independent, and you can see the text for that. Now, if you have n events, for example, 3 events or 5 or 10, we say that those events are independent if they are pairwise independent, 3-way independent, 4-way independent, and so on up to n-way independent. In other words, the probability of any AND is the product of the individual probabilities. Okay, so that's an example of independence, 2-way independence, not 3-way independent. Okay, we'll come back. Let's do an application of independence, a very interesting application.